We can now move to topic number 2. And I think some of you addressed already this question. It's the system calibration. Again, I need a sensor that has accuracy, precision, and repeatability. And I need to know if the sensor, how the sensor was calibrated, if it needs another calibration. Can I know from the system that something is going on? And what is the impact of the calibration, or shall I say the absence of calibration, on the diagnostic, especially ratios? We all know, and I'm used to have that kind of question, so I prefer to address it right now, that you don't do any kind of analysis when you have 2 to 4 ppms. I have plenty of people who draw on the Duval's triangles or pentagons. They draw the points and they call me, wow, we have a major issue. No, look at the numbers. You have 2 ppms of hydrogen, 5 ppms of CH4, it's nothing. So if you only use the Excel file I gave you, only had 1 ppm, and you see the point moving so much that it means nothing. So the topic right now is the system calibration. As a user, do I do to know that the system is still calibrated? Does it need any extra calibration? So we're starting by you.
Okay, so for Photoacoustic, one of the technologies that we use in GE, we calibrate the module, the Photoacoustic module at the factory, and we use very traceable tools to calibrate the module. And because of the technique that we use, that we will not go into detail, I don't need the slides now, I think it's okay. It does not require any field calibration. So that's, we see that's as an advantage, even though some customers, they prefer to have this, somehow this check-in or this assurance that their units or their monitors are traceable to the standards. Due to the fact of the technique that doesn't drift over the time, we don't require that. So how we ensure that the unit is following the accuracy that we specify is that because we do some testing of the different elements of the module, of the sensor. So with that, before we do any measurements, we ensure that they are operating in the right levels and ensure that they will perform. If there's any different signal that we can catch up, then we can understand and we can fight let's say an error message to understand that the module is not measuring as it should do. So in this case, actually, our approach as well is that many of our customers, they use their own labs, and we all know that the labs, they don't exactly match each other. So even though they are all traceable and they follow these intercomparations oftenly, labs results don't usually match. So our approach here is, instead of forcing our customer to adjust their history and the logs to the monitoring, is that we are capable, if the customer likes to adjust the monitoring in order to be online with the history result they got from the lab.
Thank you. Karsten?
Yeah, okay. I think, but maybe we can put on the second or third slide of my presentation. I think we all, as a online DGA industry, I think maybe we have not been perfectly honest over the last years when talking to our customers when it comes to accuracy, precision, repeatability, calibration of our devices. And I am basically showing here on that slide what is called a fishbone diagram. So everyone who is ISO 17025 accredited for any kind of measurement knows what that means. You have to put together all the different aspects of which influence uncertainty. And it has been mentioned by one of my colleagues on the table before. When it comes to online DGA, there are a lot of factors impacting on the overall uncertainty. And that's not only the gas measurement. it's in particular the gas extraction, and it's also in particular the factory calibration and the uncertainty of the certified reference material which we are using for the calibration. So all these factors together, they form the total uncertainty. We know that there is some DGA equipment, mainly gas chromatographically based devices, which can do regular calibration. But what is actually calibrated? It's calibrated mainly the gas measurement part. And the gas measurement part only contributes to a very, very small amount to the total uncertainty of an online DGA. Much more contribution comes from the gas extraction. And that leads actually to the fact that devices claiming uncertainties of 5 or 10 ppm that can be put in doubt. So maybe if you just press the button one more time, here you see, for example, a typical certificate of a reference material, oil standards ranging between 5 and 15 and so on ppm. So how can you be more accurate than the reference material? Maybe the next slide. This is a gas reference, 2 ppm. So the gas part is relatively easy to be calibrated, but the gas extraction relatively difficult. And now the last slide, if you can just put it on, an excerpt from the very, very well-known IEC 6567, which compares different extraction methods with regards to the uncertainties. And here we see that especially the gas extraction is a major contributor to the uncertainty of an online DGA, and that no one has shown to me the right solution how to calibrate that really in the field. So if we just can move to the next slide. Yeah, that one you can skip. Next one. Okay, so what we have done, we have built into our devices a very simple way how the operator can calibrate the device itself without the need to send the device back to the factory. So the operator can, on the left side, enter laboratory results taken in the field into the device, and that will change slightly the conversion function implemented in the equipment. And that makes the calibration very, very easy, although, and I fully agree with my colleague on the left side, normally infrared technology doesn't require regular calibration, but if for whatever reason you need to calibrate, you can do that in the devices very easy. Thank you.
Thank you.
There we go. Can I ask to have the second slide for my presentation? Thank you very much. There we go. So I would like to show you exactly how do we calibrate the systems in our factory, okay? A calibration in the field is not required in the normal process, okay? But I want to show you exactly how do we calibrate the systems in our factory. So basically, the very first thing we do, okay, and the test for one DGA lasts 5 days before he leaves the factory, okay? The very first thing that we do is to make the calibration on the gas space. We have very strict rules on that in terms of accuracy and repeatability. And they are visible to everyone when we send the instrument, okay? So we're talking about 2% accuracy and 1% repeatability, okay? This is in the gas space. It has been mentioned before, okay? Sometimes when we see also the data sheets from the vendors, etc., someone says accuracy without specifying if it is in oil or the gas. Someone specifies that. So we are talking here about gas space, all right? We use different level of gases using the BOC battle. So we do this at low level of gases and high level of gases with pure and mixed gases. It's quite a long and strict process that we put in place after 20 years of experience, all right? What we do then, we put the gas module inside the unit and we put this in the oil loop for days. And there is a golden unit in the oil loop which is continuously sampled and the samples are sent to external laboratory. For example, we use DGA H2B at the moment, okay? Someone asked if we can sell the golden unit. No, it's not sellable. But the golden unit gives the reference to all the other units in the oil loop, okay? With continuous sampling. So this is the way we calibrate. Say that in some countries, we have to do similar process, but using other laboratories, because, for example, in Far East or Latin America, there is no question. Their lab is the truth, okay? We do it, of course, no question about. Say that it is possible for the user to do a sort of gas sensitivity check, it's not a calibration, using a conventional BOC bottle with a mix of gas. You can inject this in the field, in the gas space, and check the sensitivity. This applies to both the photoacoustic and NDIR. Thanks.
Thank you.
Okay, so I don't have any slides, but I could refer to some of the slides just shown. So the first thing is in relation to how the system is calibrated. This is a pretty common technique, right? All of the monitors are compared to each other, and you ensure that you have good stability and good repeatability. One of the key differentiations between gas chromatography and infrared-based systems, and I've mentioned it already, but just to reiterate, is you take that monitor out of the factory and you ship it to Caracas. It sits in a box for 12 months in Caracas, and then it gets installed on a transformer after a 36-hour car journey. And that calibration that was set in the factory may not be entirely accurate anymore. So with a gas chromatography system, you recalibrate it there and then. And true, there is variability, and we've seen on Karsten's slide, there is some variability then between the calibration gas standard. So the calibration gas standard being a physical standard, being a traceable physical standard, and the extraction system. But it is very easy to see if you have a calibrated detector, it's very easy to see the differences then in repeatability because you're getting a continuous stream of data out of these instruments. So if you use gas chromatography, you can generally see repeatability plus or minus 2%, and it's on the basis of accuracy that has been determined with a gravimetrically created gas mixture, so absolute accuracies there, plus minus 2% accuracies, 3 or 4 days ago. So these systems that are based on gas chromatography are always operating off a stable calibration, whereas infrared-based systems are operating off a calibration that happened in another country, on another continent, at some point in the past. And I will admit, having been in that part of the industry, that photoacoustics is quite accurate. But is it accurate enough when you're making decisions about your transformer? Is it enough to say this is an approximation? If all you want is an approximation and all you want is an alarm that you then back up by sending the sample to the laboratory, why have you spent all this money putting multi-gas online DGA in place in the first place? Put a single gas monitor in place. It'll do the same. It'll give you an alarm and you'll send a sample to the laboratory. If you've got to rely on that, then you're missing some of the value of online dissolved gas analysis.
If I can just add something. Yeah, for sure, when you have a fault in a transformer, you're not talking about 2 or 3 ppms. You clearly have all the gases that go up. And then, I don't think it's an issue. The sensitivity or the exact value is no longer an issue. I can tell you by experience that unfortunately the ratio are not too much moved by the accuracy, especially when you have a real fault, because you see all the trend in the gases go very high, very up. So I would say it's not an issue at that point when you have a real fault.
And I'm inclined to agree to some extent. The only thing that I will say in that regard is, which is better, to have accurate data or inaccurate data?
Okay. Tony?
Would you be so kind as to put the previous slide back on again? So, in response to August Chairman's comment about all of the gases rising,
What he's saying really, correct me if I'm wrong, is that we're using the device as a detector. Everything's gone up. We don't need accuracy. What I would say then is don't spend tens of thousands of dollars on this multi-gas device. I would copy Donal and say get something less expensive because it will respond in the same way and it will give you an indication. This is me as the asset manager. I want to have a device. So in the lower left, we have an example of a chart where the DGA has not risen by a huge amount. Its one gas has risen by some parts per million, and this was used to identify and diagnose a problem. This is using a detector that produces values for hydrogen and carbon monoxide. We're going to do something with that because it's accurate. The discussion around calibration really leads into a discussion of what we call the 3 C's of DGA. The next slide, please. And so the first thing is calibration. We're interested in an instrument. So when Karsten said 15% is what we get from laboratory, I would change laboratory. So the last point on the line is instrument check with true north. Doble's Morgan Schaffer laboratory provides samples which are plus or minus 5%. We expect them to be plus or minus 5%. We expect our laboratory system in the field to give us the same level of accuracy. We will only quote to 10% normally. So in calibration, we need to look at the whole system and how that can be verified, right the way back with the DGA from a laboratory which can produce such samples. We also need to have the calibration so that we can watch for drift over time. We provide the samples to do that. And then we have to compare with the oil from the original transformer. If the original oil has no acetylene and then has one part of acetylene, I want to know that because I'm not looking for just the trend, the detection. I want diagnostics and I want them at low levels before it becomes a watch out for the low Earth orbit pieces of my transformer. Related to that, 2 other things. The carrier gas approach means you've controlled the gas which is going through the cell. The cell is going to take gas which is from the transformer, dissolved in oil, and we'll add that to the carrier gas. We'll also have moisture within the transformer. Those substances can affect the way the sensors work. If I have a sensor which is providing GC, they are part of the measurement. They will go through the columns, we will detect them, we'll measure them. If we're going to go through a cell which is a headspace cell and using infrared, there'll be reflective paths, and any contaminants were going to be condensed on the mirrors. You'll get oil. We found this to our cost when we developed our own portable FTIR system. And you'll also get moisture. These will affect the way the system operates. To remove those, you need to have a filter. That filter is a maintainable device. It's consumable. If you don't have that device as part of your consumables, you're going to have drift due to the interference condensing on the mirror. So you have to be very careful. The last point I'd make on this particular section is the stability. We operate the devices we sell continuously. So if you say we want the measurement every 12 hours, we still measure continuously. If you want it every 4 hours, we still measure continuously. And the reason for that is so that we don't switch on and switch off. That will change the electronics. That causes drift in the electronics. It causes drift in the whole measurement system. To go with that, we don't just keep the temperature of the cell where the measurement is made controlled. We control the whole environment. So we're plus or minus 1 to 0.5 a degree. This means that the measurements are consistent. I want a result so that when I don't get 200 parts of acetylene, I get 1, I can trust the result. That to me is what I'm going to spend the money for. If I'm not going to do that, I will buy the less expensive 1-gas, 2-gas device. So the 3 C's, there's the contamination, there's the calibration, and then there's the consumables. All of those are part of the overall cost, which is the lead into the next slide. And we need to maintain a focus on what decision we are trying to make. As an asset manager, I'm going to decide whether to send someone out or not. By the way, if that happens to be a 6-hour flight and a 10-hour drive, or a 10-hour train journey to the station, I want to make sure that they're there for a good reason. I'll stop talking now.
Thank you very much. For sure, whatever the gas analyzer, I will not send anyone to take a sample when I detect that something is going wrong, and this is my demand. So I do have to trust the analyzer whenever it works. I really need to trust the information that is coming out of the analyzer.